In this lecture, we will learn voltage divider configuration. This configuration is the most widely used biasing scheme. I will explain why voltage divider configuration is preferred over other biasing schemes. And you can see in this circuit, we have resistance Re, we have resistance Rc, but there is no resistance Rb. In place of resistance Rb, we have two other resistances R1 and R2, and because of this we have to use Thevenin's theorem. I hope you know how to use Thevenin's theorem. If you don't know or don't remember how to use Thevenin's theorem, you may refer the small introduction displayed on the screen. In this circuit, potential at this point is equal to VCC and potential at this point is also equal to VCC. So we can modify this circuit. In which potential at this point is equal to VCC, or we can say plus VCC, and potential at this point is also equal to plus VCC. First we will find out the operating point in case of voltage divider configuration, and after this I will explain why we prefer voltage divider configuration. In order to calculate the operating point, we must draw the equivalent circuit by using the Thevenin's theorem, and in case of Thevenin's theorem, the equivalent circuit is having the Thevenin's resistance. The Thevenin's resistance is represented by R sub Th, and we have the Thevenin's voltage. The Thevenin's voltage is Vth, and then we have the load resistance. And in case of voltage divider configuration, the load is this side, so the equivalent model will look something like this. This is the Thevenin's voltage Vth, and this is the Thevenin's resistance Rth, and once we have the value of Thevenin's resistance Rth and Thevenin's voltage Vth, we can easily calculate the collector current IC and the output voltage VCE. So the first thing that we have to do is to find out Rth and Vth. For this I will use this circuit, and we will draw this circuit in different manner. Instead of having the potential at point VCC, I will try to convert it to the potential difference, and for this purpose I will paste this circuit again. And we already know potential of ground is equal to 0 volts, so I will replace the ground with the negative terminal, and I will replace VCC with the positive terminal. So the circuit will look something like this. This is the potential difference, and it is equal to VCC. The negative terminal is connected to the ground because potential of ground is equal to 0 volts, and the negative terminal stands for the lower potential. Now we can easily calculate the Thevenin's resistance Rth and the Thevenin's voltage Vth. First I will calculate the Thevenin's resistance, and then we will calculate the Thevenin's voltage. In order to calculate the Thevenin's resistance, we need to short circuit all the voltage sources. We only have one voltage source, so we will short circuit VCC, and then we have to open circuit the load. This is the load, so we will open circuit it, and once we do these two things, we have resistance R1 connected in parallel with the resistance R2. The load is open circuited, and VCC is short circuited. This is resistance R1, resistance R2, and the equivalent resistance is nothing but the Thevenin's resistance. The two resistances are in parallel, so Rth is equal to R1 parallel R2, or we can say R1 multiplied with R2 divided by R1 plus R2. So this is the value of Thevenin's resistance. Now we will calculate Thevenin's voltage, and in order to calculate Thevenin's voltage, we need to calculate current in this loop. But before that, I will remove this short circuit, and now we will calculate the current in this loop. And once we have current in this loop, we have to find out voltage across the load, or simply we can find out voltage across resistance R2. The current is, let's say, I, and the current I is equal to VCC divided by R1 plus R2 you can use KVL to find this value. And to find out drop across resistance R2, or simply VTH, we need to multiply current with resistance R2. This is the drop across the resistance R2. So VTH is equal to IR2, or simply R2 VCC divided by R1 plus R2. So this is the value of VTH, and we have already calculated RTH. Now we can find out current IC and voltage VCE. When you see this circuit closely, you will find this is nothing special but ammeter bias configuration. The only difference is resistance RTH and voltage VTH. In case of ammeter bias resistance, we had resistance RB in place of RTH, and in place of VTH we had VCC. We can also redraw this circuit, in which instead of taking VTH as potential difference, we can take it as potential at point. And you can clearly see this circuit is ammeter bias configuration with RTH in place of RB and VTH in place of VCC. In order to calculate current IC, we must calculate the base current first. And to calculate base current, I will apply Kirchhoff's voltage law in the input loop. So we have VTH minus IB RTH drop across this resistance minus VBE minus IERE drop across ammeter resistance equal to 0. And we already know the current IE is equal to beta plus 1 times IB. So we can write this equation like this: IB RTH minus VBE minus beta plus 1 times IBRE equal to 0. I will take IB common from these two terms, and finally the current IB is equal to VTH minus VBE. VBE is equal to 0.7 volts for silicon transistor, and in the denominator we have RTH plus beta plus 1 times RE, and the collector current IC is equal to beta times IB. So IC is equal to beta times VTH minus VBE divided by RTH plus beta plus 1 times RE. So you can see in the expression of collector current, in place of VCC we have VTH, and in place of RB we have RTH, and the remaining things are similar to the ammeter bias configuration. And you already know the condition to make IC independent of beta. If Thevenin's resistance RTH is smaller than beta plus 1 times RE, if we have this condition, then the current IC is independent of beta, because beta will cancel out from numerator and denominator, and the expression will not have beta value. The next thing is the calculation of voltage VCE, and for this I will apply Kirchhoff's voltage law in the output loop. So we have VCC minus ICRC, because ICRC is the drop across resistance RC. Then we have minus VCE minus IERE drop across the ammeter resistance is equal to IERE equal to 0. So this is the equation, and by using this equation we will calculate the voltage VCE. The ammeter current IE is nearly equal to the collector current, so we will replace ammeter current by the collector current, and we have VCC minus IC inside the bracket RC plus RE minus VCE equal to 0, and finally we have VCE equal to VCC minus IC RC plus RE. So this is the final expression of the voltage VCE, and this is the output voltage. Once we have the base current IB, we can easily calculate the collector current by multiplying beta to the value of IB, and once we have IC, we will put it here and we can easily calculate the voltage VCE. So this is all about the calculation of operating point. The last topic in this presentation is the advantages of voltage divider configuration. Voltage divider configuration is mostly used because we have RTH. RTH is the combination of R1 and R2, and to make IC independent of beta, we have to follow this condition. And in other cases, or you can say in other biasing schemes, we have the condition according to which RB must be smaller than beta plus 1 times RE. And if we compare the two conditions, there is only difference of RTH and RB. In this case we have RTH, whereas in this case we have RB. RTH is the parallel combination of R1 and R2, whereas RB is the single resistance, and it is better to use RTH instead of RB because RTH is always smaller than R1 and R2. This is the property of parallel combination, and to satisfy this condition RTH must be small, and we are getting a small RTH without making R1 and R2 very small. On the other hand, we only have one resistance in this condition, and we cannot decrease RB beyond certain value because there are disadvantages on decreasing RB beyond a certain value, and because of this it is good to use voltage divider configuration as we have flexibility in designing due to two resistances. So this is all for this lecture. In the next lecture we will solve one numerical problem based on voltage divider configuration. So see you in the next lecture.